scenario being demonstrated is the impact that the reservoir effect can have when carrying out a soundness test on an existing natural gas installation using the fuel gas as the test medium. For the purposes of the demonstration, we have set up a mock 4-bar gas service and are utilizing 4 meters of polyethylene pipe as our downstream installation pipework. To illustrate the reservoir effect, we have fitted a digital pressure gauge onto the service inlet pipe. The equipment used to demonstrate this process is as follows: a mock 4-bar gas service with a T-piece fitted after the customer isolation valve to enable connection of the digital pressure gauge. This T-piece and gauge would not normally be part of a gas service inlet pipe. A 2-stage pressure reduction regulator which has a reset facility to energize the system with gas. Also, the set point of this regulator is 22 millibars. A domestic gas meter. A single-column liquid-filled gauge to carry out a soundness test. Downstream supply pipe, not normally polyethylene, this is being used for ease of demonstration only. And leak detection fluid. As you can see, there is no pressure in the downstream installation pipework until you depress the reset button on the regulator. On this model of regulator, the reset button is a red button. On other models, the reset button may be green or white and may be a lever rather than a button. The installation is now pressurized. If we now look at the start of the test period, at the 3 key elements, we have visible pressure dropping on our digi-gauge on the service inlet pipe, a leak on the installation bubbling away, and crucially, a rock-solid reading of 22 millibars on the potty meter. Current standard requirements for testing an existing natural gas installation using the fuel gas are 20 millibar pressure, 2 minutes stabilization period, 2 minutes test time. So, with the clock ticking, we will observe the impact of the reservoir effect on the test as time passes. After 6 minutes has passed, we can see that although the leak has been evident from the start, we still have a reading of 22 millibars on the potty meter. You can also see that the pressure in the reservoir is dropping and is currently at 2768 millibars. This shows that it is the reservoir of pressure that is maintaining the pressure of 22 millibars in the installation, effectively masking the leak. After 12 minutes has passed, we can see that although the leak has been evident from the start, we still have a reading of 22 millibars on the potty meter. You can also see that the pressure in the reservoir is continuing to drop and is currently at 1432 millibars. This shows that it is the reservoir of pressure that is still maintaining the pressure of 22 millibars in the installation. After 18 minutes has passed, you can see that the pressure in the reservoir, as shown on the digi-gauge, has dropped to 19 millibars. We can also see that the pressure in the installation, as shown on the potty meter, is dropping in direct proportion to the visible leak. The rate of leakage on the installation in this demonstration would result in a complete drop in pressure in less than 2 minutes. The key learning point of this demonstration is that the leak will not become evident until the pressure in the reservoir has dropped below the set point of the regulator. It is very important that the reservoir effect is understood and dealt with appropriately.